All right, I'm Matt Haffner. I'll be chairing our second session here. We're going to move a little closer to home. Topic will be Milky Way galaxy and surroundings. To start us off, just a reminder, all the talks in this session will be 15 minutes, 12 minutes for the talk and 3 for questions. And to start us off will be Chad Bustard, a versatile family of galactic wind models.
All right, can everyone hear me okay? Okay. All right, well, I'm Chad Bustard. I'm another grad student here at UW-Madison. And I'm going to tell you about some galactic wind models we've been working on here. So this is work I've been doing with my advisors, Ellen Zweibel, Elena Diongia, and also with a seemingly growing army of eager undergrads, including Corey Cotter. So the model I'm going to tell you about is based on the 1985 Chevalier and Clegg model. So this model is a spherically symmetric, so 1D model of galactic outflows, where there's a constant rate of mass and energy injection into the outflow from supernovae. And this occurs out until some radius r, big R, which is the radius of the galaxy or radius of the starburst region. And then after this radius, the mass and energy injection drops to 0. So what they do in this paper is they solve 3 equations. They solve the mass conservation, momentum conservation, and energy conservation equations. And that allows them to get a fairly simple looking expression for the Mach number of the outflow. So let me mention a few things about this model that made us uneasy. One is that this expression for the Mach number is analytic in 2 different regions, but it's not actually analytic at the critical radius r. Another is that when they did this paper, they really wanted to compare their model to M82. And M82 is a typical galactic wind example, but it's also a very strong galactic wind. So one that is so strong that gravity really doesn't need to be included in the model. So what they do is they take out this gravitational term, but we're going to put that back in. So our model keeps in the same vein of being simple and versatile by being spherically symmetric, but we include a gravitational potential from an extended mass distribution. Instead of having a constant mass and energy source out to some radius, we now have a mass and energy injection that allows you to have more mass and energy injected towards the center of the galaxy and less towards the edges. And I think most importantly, we include radiative losses, which, as I'll show you, is actually a very, very important thing. So the way we did this is we made an analytic fit to the cooling function between about 10 to the 4 and 10 to the 8 or 10 to the 9 Kelvin. And the most important thing, for me at least, to see from this plot is that the peak is about 10 to the 5 or 10 to the 6 Kelvin. So if you have an outflow that has temperatures greater than 10 to the 6 Kelvin, radiative losses may not be so important, but that wind will probably adiabatically cool into this region where radiative losses are very important. So let me say a little bit more about this. Radiative losses in general result in a decrease in the temperature. So here I've plotted temperature profiles versus radius for a number of different wind solutions. And what we can see for different mass loading factors beta is that you have a lot of solutions that go out to almost the radius of the galaxy and then drop very sharply. So it's a catastrophic loss in temperature. And we're finding that these solutions are actually very abundant, so we see these everywhere. And another thing we can somewhat see from this plot is that winds with high mass loading, high beta, cannot usually be driven at low central temperatures. So that means that you need to have more initial thermal energy to drive those outflows. So you can see this from a plot here that our undergrad Corey Cotter made. So this is plotting the parameter space of alpha, energy loading factor, and beta, mass loading factor. And what we're plotting here is the central temperature of the outflow required for the wind to have a velocity greater than the escape velocity. So this is you can think of this plot as the thermal energy required to have an outflow that escapes the galaxy, which is what we're most interested in for right now. So you can see that if you have high beta and low alpha, then you need to have much more thermal energy to drive that outflow. But if you go towards high alpha, so more energy injected and less mass loaded, then radiative losses aren't nearly as important, and you can drive an outflow much more easily. So this leads us to another question which helps me to build some physical intuition, and that's which outflows are most efficient. So what I've done here is I've plotted a number of different galactic wind solutions, and each of them have the same central temperature. So here we have, I'm plotting velocity, I'm also plotting sound speed, so this top curve here for velocity and this sound speed curve here in red are the same wind run for our model. So looking at these two solutions again, what we find is that you get the highest velocity and also the highest temperature when you have high energy loading and low mass loading. If you instead did low energy loading and high mass loading, then you would get a wind solution that has a much lower velocity and also a much lower temperature. So in some sense, these winds are the least efficient in expelling mass from an outflow. But again, we also see that there are many solutions here that give very, very low temperature outflows. So in these black dashed lines, I've plotted a few solutions where the temperature drops to below 10 to the 4 Kelvin, even within 4 to 500 parsecs. So this is something that we want to focus on more in the future, but below this 10 to the 4 Kelvin, our assumption of collisional ionization equilibrium breaks down, and it'd be interesting for us to include photoionization heating. We also wanted to compare to some observations. So what we did is we looked at data from Mineo 2014, and what they did was they had a large sample of starburst galaxies, and they plotted the star formation rate and the X-ray luminosity of those galaxies. So the best fit line is this black line here, and that black line corresponds to this top blue line in my plot here. So this is plotting the total luminosity of the galaxy, but we don't expect that all of that luminosity comes from the wind or diffuse sources. So the fraction of diffuse emission is given by these other blue lines here. So this would be for 1/10 of that total emission, this would be 1/100th. And what we want to do is see how our model compares to the Chevalier and Clegg model and reproducing this linear relationship between luminosity and star formation rate. So what we've done is we've plotted the Chevalier and Clegg model here, and that is a model that has a quadratic relationship between luminosity and star formation rate. And we've plotted one of our models here. You can see that it has a much better, in the sense that it's more linear relationship between X-ray luminosity and star formation rate. Now there's a few things you have to do to get this linear relationship with our model. One is you need to include some sort of relationship between the mass of the galaxy and the star formation rate, so that for higher star-forming galaxies, the mass is also higher. So this is not something that would make any difference for the Chevalier and Clegg model, because that model did not include any sort of gravitational potential. But the fact that we've included mass means that there will be a difference, and that this will make a large difference. The main requirement to get this linear relationship across such a large range of star formation rates is to include an inverse relationship between mass loading factor and the star formation rate, or galaxy mass. So we say that for low mass galaxies, the mass loading is greater, and for high mass galaxies, the mass loading is lower. And this is something that I believe is being seen in observations as well as in galaxy formation simulations. So we can make a few conclusions just off these first couple of slides. One is that the efficiency of the outflow and expelling mass depends a lot on the mass loading and energy loading, specifically the solutions with the lowest mass loading and highest energy loading are, in a sense, the most efficient. We've talked about the importance of radiative losses and how they lead to an abundance of low temperature outflows. And we've also been able to match the observed X-ray luminosity star formation rate relationship with the large necessity that you need to have an inverse relationship between the mass loading and the star formation rate. So I also believe that these toy models are very interesting, insightful, and versatile, and they can lend themselves to a lot of different problems. So we have a lot of future work planned, and some that we've started already that I would really love to talk to people about offline after this talk. One is we want to include a cosmic ray wing component to see how that affects our solutions. We also have an undergrad who's going to work on this in the fall, doing time-dependent wind solutions with a self-consistent feedback model. We've looked a bit at photoionization heating, but we think that could be very important for these low-temperature winds because it could provide a source of heating that would kind of flatten out the temperature profile that right now adiabatically cools further and further. We want to look at non-equilibrium ionization, and we also want to model the galactic wind termination shock. So in my last minute or two, I want to talk about modeling the galactic wind termination shock. And you can do this in a fairly simple way using our model. You can find the total pressure of the wind. When you set that equal to the pressure of the surrounding IgM, the wind will form a termination shock. Our model can give densities, temperatures, velocities, sound speeds, and we're able to get the compression ratio at that shock. We can see how some sort of assumption on the magnetic field plays into that shock and how it affects the compression ratio. And we think it could be really interesting to look at the observational implications of this termination shock, because also it could act as a very good heat source for CGM material. Another thing that I've been looking at a bit lately is making estimates of how you can accelerate cosmic rays using this galactic wind termination shock. So it's been proposed that you can accelerate cosmic rays to energies greater than 10 to the 17 eV, and we are currently making some estimates to see how valid that would be. So with that, I will leave you with a picture of the cosmic ray spectrum and why it's important to look at where these cosmic rays come from and how they could come from a galactic wind termination shock. It's because we know fairly well where these cosmic rays come from. They come from galactic sources. We know fairly well where the high energy cosmic rays come from. They come from extragalactic sources. But there's a little region here where it's not completely nailed down where these cosmic rays come from. And with that, I'll take any questions. Thank you.
Let's start over there. And there was a hand up over here. We can get over. You can shout.
You must know the answer to this off the cuff, but so you showed very actively star-forming galaxies in the SFR-LX correlation, but I had the impression that a lot of the winds in those very extreme galaxies were driven by AGN. So should your models be applying to the?
Not necessarily, and I don't know how much I can comment on the actual data in that Mineo paper, but for this, we use this plot from 0.1 or 1 star formation rate all the way to 1,000 to follow another group's previous work that had done the same thing. So it's nice that we can show that our winds actually give a linear relationship all the way to 1,000, but you don't necessarily expect to have that for a galactic wind.
Thank you. It can be that galactic winds are different from, say, stellar winds, in that the stellar winds start with zero velocity and they are thermally driven, right? In the galaxies, the hot gas which flows out, we can have initial velocity, the kick from the supernovae. So at the edge of the disk, the velocity can be already supersonic, say 100 kilometers per second. So what's your boundary condition? I guess velocity equal to 0, right? What if you make the initial boundary condition velocity equal to 100 kilometers per second? It can dramatically change the dynamics of the wind, won't it?
Right, and we have not played around with that much. Our boundary conditions are that the velocity goes to 0 basically at the center of the galaxy, which we say is 5 or 10 parsecs, something very small.
Do you plan to also to consider different boundary conditions?
Yes, oh yeah, we can definitely consider that, absolutely.
2 rows back. And then Chris, and then we'll have to wrap up.
Would it be possible to include several phases in your model? So the wind is propagating in something which comprises many
That is something we
densities.
definitely would like to do. That's not something that we've done right now, but that's definitely something that we would like to do, yes.
Because it seems important to compare to observations.
Right, absolutely.
Yeah, you showed that you get very good agreement between the theoretical and observed luminosity of the X-rays. What about the temperature? If I interpreted your interboundary condition, it seemed to me that you had to start off at a very high temperature order, 10 to the 8th Kelvin. That's 10 kilovolt gas at the base, and that would then be, I thought, hotter than the observed X-rays. So could you comment?
So we don't need to start off with temperature as high as 10 to the 8. No, you can get a number of solutions that start off much lower. So here are a few that start off more around 10 to the 6.
I see, okay.
It depends a lot on the mass loading factor as well.
All right, let's thank Chad one more time.